What if everything we see, every galaxy, every star, every atom, is not the whole universe, but the inside of something much larger? For decades, black holes have been thought of as cosmic dead ends, regions of space where matter falls in and never returns. But a growing number of physicists are asking a far stranger question. What if a black hole is not an end, but a beginning? What if our universe itself was born from the collapse of a star in another universe? And everything we experience exists on the inside of a black hole. This idea sounds like science fiction, but it emerges from real equations, real observations, and real problems in modern cosmology. Tonight, we are going to explore one of the most radical possibilities ever considered about the nature of reality. And by the end, the universe may feel a little more unsettling and a lot more mysterious than before. So let us start with the simplest question of all. What exactly is a black hole? Really? To understand the idea that our universe could exist inside a black hole, we first need to be very precise about what a black hole actually is. In popular imagination, black holes are often pictured as massive objects, pulling everything inward with an irresistible force. But in modern physics, that picture is deeply misleading. In general relativity, a black hole is not described as a physical object at all. It is a geometric solution to Einstein's equations, a region where the geometry of spacetime is curved so extremely that all possible paths point inward. There is no new or special gravitational force inside a black hole. Objects fall inward for the same reason. Planets orbit stars. Their motion is determined entirely by the shape of spacetime itself. This brings us to one of the most misunderstood features of a black hole: the event horizon. The event horizon is not a physical surface or a solid boundary. It is a causal boundary, a point beyond which no signal can reach the outside universe. A photon crossing the event horizon is not suddenly stopped or blocked. Instead, there simply no longer exists any path that leads outward. A useful analogy is the surface of the Earth. If you stand at the North Pole, every straight direction you walk will lead you south. There is no force pulling you south, only the geometry of the surface itself. Perhaps the most surprising fact is what happens at the moment of crossing the event horizon. For an observer falling freely, there is no sudden impact, no spike in pressure, no clear physical signal. In fact, for sufficiently massive black holes, tidal forces at the horizon can be extremely small. The larger the black hole, the gentler the space-time gradient at that boundary. Finally, there is the idea of the singularity. Singularities are often imagined as infinitely dense points of matter, but in physics, a singularity is something far more subtle. It marks a place where our mathematical models stop being able to make predictions. Rather than describing physical infinity, it tells us that our current theories are incomplete. So, if a black hole is nothing more than the geometry of spacetime taken to an extreme, what does the inside of that geometry look like mathematically? Now that we understand a black hole as geometry rather than an object, we can ask a deeper mathematical question. What actually happens in Einstein's equations when something falls into a black hole? When physicists first solved the Schwarzschild solution, it appeared that spacetime simply ended at the event horizon. But that ending turned out to be an illusion created by the choice of coordinates. When the equations are extended fully, the Schwarzschild solution does not stop at the horizon. Using Kruskal-Sekares coordinates, spacetime continues smoothly beyond that boundary. Mathematically, The horizon is not a break or a singular point. It is simply a place where our usual description fails. Once this extension is made, an unexpected structure appears. The equations allow for a region known as a white hole. A white hole is the time-reversed counterpart of a black hole, a region where matter can only move outward. While white holes are unlikely to exist as stable physical objects, their presence in the mathematics is important. It reveals that the space-time structure of a black hole is far richer than a simple one-way trap. Even more strangely, inside a black hole, the roles of space and time change. Outside the horizon, time flows forward, and radius is a spatial direction. Inside the horizon, the radial direction behaves like time itself. Moving toward the singularity becomes as unavoidable as the passage of time. You cannot stop it any more than you can stop tomorrow from arriving. This reversal opens a profound possibility. If the future inside a black hole must unfold, then space-time ahead could in principle expand. In some models, that expansion looks remarkably like the birth of a new universe. Crucially, that internal universe does not need to resemble the one it came from. The physical constants could be different. The rate of expansion could follow entirely new rules. From the inside, what we call the Big Bang might not be a beginning of everything. It could simply be a transition surface between two phases of space-time. And that leads to an unsettling question. If every black hole can give rise to a new space-time, could our own universe be showing signs of such an origin? If the idea of a universe born inside a black hole sounds speculative, the next step is to confront it with numbers. Surprisingly, this is where the hypothesis becomes uncomfortable. In general relativity, every mass has an associated Schwarzschild radius. This radius is given by a simple relation involving mass, gravity, and the speed of light. It tells us how compact an object must be to become a black hole. Now imagine applying this formula to the entire observable universe. Replace the mass with the total mass energy contained in all galaxies, radiation, and dark components we can measure. When this is done, something remarkable happens. The resulting Schwarzschild radius comes out to be on the same order as the radius of the observable universe today. Not vastly larger, not vastly smaller, just uncomfortably close. The coincidence does not stop there. Consider the average density of a black hole. Contrary to intuition, this density does not depend on how massive the black hole is. For supermassive black holes, the average density can be lower than that of water. Now compare that with the average density of the universe today. Once again, the values fall into the same order of magnitude. This is not the result of arbitrary number fitting. The inputs come directly from measured cosmological parameters. They are constrained by observations of the cosmic microwave background and by the large-scale structure revealed through baryon acoustic oscillations. In physics, coincidences like this are not dismissed lightly. Historically, uncomfortable numerical alignments often point to deeper underlying structure. They are clues that a theory is touching something real, but not yet fully understood. And that leads us to a new hint. Is this merely a mathematical coincidence, or the imprint of a deeper cosmic structure? To push this idea further, we need to look at another boundary we already accept as fundamental. The universe itself has a horizon, known as the cosmic horizon. It defines the limit of what we can ever observe. We cannot see beyond this boundary, not because nothing exists there, but because light from those regions has not had enough time to reach us. The cosmic horizon is therefore a causal limit. It separates what can influence us from what cannot. This should sound familiar. A black hole also possesses a horizon that plays exactly the same causal role. Beyond the event horizon, no information can ever reach the outside universe. The cosmic horizon and the event horizon arise from different physical situations. One comes from cosmic expansion, the other from extreme spacetime curvature. Yet at a deeper level, they share the same essence. Both represent a loss of causal contact. This parallel becomes even more striking when we consider entropy. Black holes are known to have entropy proportional to the area of their event horizon. This is not a metaphor or a mathematical trick. It is a concrete result of spacetime thermodynamics. Remarkably, the universe exhibits a similar behavior. The entropy associated with the observable universe is tied to the area of its cosmic horizon. Once again, this is not poetic language. It emerges from applying thermodynamic principles to spacetime itself. Taken together, these parallels suggest something profound. The universe may not be just space expanding over time. It may be a thermodynamic system with limited information content. A system where horizons play an active role in its fundamental behavior. At this point, the resemblance becomes difficult to dismiss. If the universe has a horizon like a black hole, does it also share black hole-like dynamics? So far, the clues we have explored were largely mathematical and theoretical. But there is another line of inquiry that comes directly from observation. It begins with one of the most fundamental assumptions in cosmology. The cosmological principle states that the universe has no preferred direction on the largest scales. It should look the same no matter where we look. A universe with a global spin would challenge this assumption. Rotation introduces a distinguished direction in space, and that would break perfect isotropy. In recent years, some galaxy surveys have reported an intriguing anomaly. Spiral galaxies appear to show a slight statistical preference in their direction of rotation. Individually, these signals are weak. They are not strong enough to claim a discovery, but they are persistent enough to make cosmologists uncomfortable. The standard cosmological model has no natural place for a global rotation. A Big Bang that is perfectly isotropic cannot generate net angular momentum. Any local spins that form later must cancel out on large scales. This makes the anomaly difficult to explain within the usual framework. If such a rotation were ever confirmed, the consequences would be profound. It would require modifications to the lambda CDM model, or it would force us to consider boundary conditions that existed before the Big Bang. Either way, the implication is unsettling, because it suggests the universe may carry a memory of something that came before. And that leaves us with a final question. If this angular momentum is real, where did it come from? At this point, we have gathered several unsettling clues. Mathematical extensions of black holes that do not end at the horizon. Numerical coincidences between the universe and a Schwarzschild radius. Horizons that behave thermodynamically in strikingly similar ways. And now, a possible hint of rotation written into the large-scale structure of the cosmos. To connect these pieces, we need to return to a surprisingly simple result in black hole physics. It is known as the no-hair theorem. According to this theorem, a black hole is completely described by just three quantities: its mass, its electric charge, and its angular momentum. Every other detail about the matter that formed the black hole is erased. The composition of the star, the internal motions, the complex structure that once existed, all of it disappears from the external description. What remains is not information about matter, but information about spacetime itself. This is where angular momentum becomes special. Unlike most details, spin is not something that can simply vanish. Angular momentum is a conserved quantity. When matter carrying spin collapses into a black hole, that spin does not end. It becomes encoded into the geometry of spacetime. The black hole itself rotates. More precisely, spacetime around it is dragged into rotation. This effect is known as frame dragging. Crucially, this rotation does not stop at the event horizon. The horizon does not destroy angular momentum. It only hides it from the outside observer. From the mathematical point of view, spin becomes a global property of the interior spacetime. Now consider what happens if a new spacetime emerges beyond that horizon. If a black hole gives rise to a baby universe, that universe cannot start from nothing. It must inherit the conserved quantities of its parent. Mass may be transformed into expansion energy. Charge may neutralize. But angular momentum has nowhere to go. It must pass through. In such a picture, the interior universe would inherit a spin, not a violent rotation, not something that dominates its dynamics, but a weak, global, coherent angular momentum spread across the entire spacetime. This immediately explains a key puzzle. If the universe has a spin, why is it so difficult to detect? Because it is not large. It is not something that would produce obvious swirling patterns. Instead, it would appear only as a subtle statistical bias. Exactly the kind of signal hinted at in galaxy rotation surveys. Too weak to stand alone as proof, but too structured to be easily dismissed as noise. In this view, the weakness of the signal is not a problem. It is a feature, a fingerprint rather than a signature. Something inherited rather than created. The picture that emerges is unexpectedly coherent. Black holes erase details but preserve deep structure. Horizons hide information but do not destroy it. And a universe born from such a process would carry subtle traces of its origin. At this stage, the idea no longer feels like a collection of coincidences. It begins to resemble a consistent physical narrative, one where the same principles apply across vastly different scales, and where our universe may be less isolated than we once believed. Which leads us to a final reflection. If our universe is the descendant of a black hole, what does that change? So where does this leave us? The honest answer is simple. There is no definitive evidence that our universe was born inside a black hole. But there is also no measurement that has fully ruled the idea out. What this idea really does is force us to re-examine some of our deepest assumptions. In particular, the notion that the Big Bang must represent an absolute beginning. From this perspective, the Big Bang may not have been the start of everything. It may have been a transition, a change in the structure of space-time itself. That shift in perspective carries deeper implications. It suggests that our universe may not be alone, that black holes may not simply be cosmic dead ends, but mechanisms through which new universes can emerge. In that picture, destruction and creation are not opposites. They are parts of the same process, viewed from different sides of a horizon. If ideas like this resonate with you, ideas where physics approaches the edge of imagination, yet remains anchored in real equations and real data, then consider subscribing to the channel. There is much more to explore. And perhaps one final thought is worth leaving you with. Somewhere in the universe, countless black holes are quietly forming. We see them as regions of collapse and loss, but it is possible that each one marks a beginning we can never observe, a future hidden forever behind a horizon. And if that is true, then the universe may be far more fertile and far more mysterious than we ever imagined.